Lesson 16 is key features from rules of quartic functions. Technically, lesson 16 has like three different workbooks, but I felt like it was okay for the video to like combine all the concepts. So 16.1 and 16.2 are like finding key features. So 16.1 is like intercepts and zeros. 16.2 is end behavior where it's positive, negative, relative, max, or min. And then 16.3 is graphing. So we're just going to take all of those concepts and kind of look at them at a single time, and it'll flow a little bit better that way. So example 1, find the following key features of the function, then sketch the graph of the function. So it's f of x equals negative x minus 4 times x plus 1 times x plus 2.5 times x minus 3. If I want to find a y-intercept, I have to find f of 0. So I have to find like what the value of the function is when x equals 0. So I would do f of 0 is equal to, and that means that I take a 0 and I put it in the function where all of the x's are, because 0 is going to be my input value. That's always how you can find a y-intercept, especially if the function's like not in standard form. In standard form, you can usually just look at the constant function, but this one is not. Okay, so it'll be f of 0 is equal to, don't forget about this negative sign there. Sometimes it's easy to miss those. So negative, and then I was gonna say you can do it in your head if you want to. I'll write it all out like with the zeros going in for each one. But if you're like, okay, I know 0 minus 4 is negative 4, just put negative 4. But just to see us like putting them all in, it'll be 0 minus 4 times 0 plus 1 times 0 plus 2.5 times 0 minus 3. Okay, so I took the 0 and I replaced all of my x's with 0, and then now I just have to simplify, and that will give me my y-intercept, so the negative out in front. And then 0 minus 4 is negative 4, 0 plus 1 is 1, 0 plus 2.5 is 2.5, and 0 minus 3 is negative 3. And then now we can just go ahead and multiply them all together. I don't really like messing with negatives a lot of times with the calculator, especially if you're using like a phone calculator. I feel like it's pretty easy to like get messed up. So I just like to count the negatives. So we have 1, 2, 3 negatives. So if you have an odd amount of negatives, your product will be negative. If you had an even amount, then your product would be positive. And then now we don't have to worry about like multiplying in the negatives. We'll just do 4 times 1 is 4 times 2.5 and then times 3. So altogether it's 30 and it's negative 30 since we had an odd amount of negatives. So that's my y-intercept. I just want to write it as like a point. So if you picture like on an x and y axis, a y-intercept of negative 30 would be 0 for x, and then negative 30. It's also like a nice reminder because like, you know, we put 0 in for x to find this number. So 0 must be the x coordinate as opposed to the y coordinate. So 0, negative 30. And then to find the zeros of the function, that means that we like take 0 and like completely replace f of x with it. So I'll rewrite the function with 0 in for f of x. So it'd be 0 equals negative x minus 4 times x plus 1 times x plus 2.5 times x minus 3. And then now I'm solving for x. So I want to figure out like what value for x makes this true. So this is already in factored form, so like the harder part of the work is already kind of done for us. Now we can just set each factor equal to 0. I don't have to do anything with the negative here because there's no like x involved with it. If there was an x out in front, I would want to set that equal to 0, but there's not, so I don't really have to worry about the negative. So I would just set each factor equal to 0. So first is x minus 4 equals 0, and then next is x plus 1 equals 0, and then x plus 2.5 equals 0, and then x minus 3 equals 0. And then we set each factor equal to 0. So we just use inverse operations. So I'll just write the one for plus 4 and the rest we'll probably just do in our head. So for x minus 4, I would have to add 4 to both sides, and that would give me an x equals positive 4. For the x plus 1, I would have to subtract the 1 over, and that would give me an x equals negative 1. For x plus 2.5, I would have to subtract 2.5 over, and that would give me an x equals negative 2.5, and then for x minus 3, I'd have to add the 3 over, and that would give me an x equals positive 3. So it's usually like, or not usually, it is just like whatever the like opposite of your factor is kind of what ends up being your 0. So like our factor was x minus 4, our 0 from it was positive 4, because you have to use inverse operations to get x by itself. So these are zeros, so x equals 4, x equals negative 1, x equals negative 2.5, and x equals 3. And remember, zeros are just like where the function is crossing the x-axis, so they're like pretty much the same as an x-intercept. We'll just write the x-intercepts as points. And then if you picture on a graph, an x-intercept is going to be obviously on the x-axis, so it'd be x, and then the y-coordinate would be 0. So if I just take like each of my zeros and make that an x-coordinate, and then the y-coordinate is 0, that would give me my x-intercepts. So it'd be 4, 0, negative 1, 0, negative 2.5, 0, and 3, 0. Each 0, like in terms of like these zeros, not like the number 0 necessarily, each 0 gets their own x-intercept. So let's see. So x equals 4 was 4, 0. X equals negative 1 was negative 1, 0. X equals negative 2.5 is negative 2.5, 0. And then x equals 3 is 3, 0. And then I'm going to jump down to end behavior, and then I'm probably going to stop and sketch before answering the rest of them. So for end behavior, we just have to look at whether the lead coefficient is positive or negative. And for quartic functions, because they are like an even power, that means that for the end behavior, either both sides are going to be going up or both sides are going to be going down, just like a quadratic, so which is x squared. So this is in factored form. So when it's in factored form, to kind of like, without having to do all the work of multiplying it all out to see what the lead coefficient is, you have to look at where it would come from. So like, if I were to multiply everything through, it would be x times x times x times x. And that would give me my like x to the 4th lead coefficient. But I have this negative right here, so it would end up being like a negative x to the 4th. So the lead coefficient is negative. Lead coefficient is negative. So that means that the function is like decreasing overall. So my end behavior would look like this. Sorry. Okay, so both sides would end up going down. That little like baby sketch right there is enough to answer the end behavior problems. So if both sides are going down, that means on both lines of like my end behavior, they're both going to be going to negative infinity. Remember, this is like, so as x approaches negative infinity, that means x is getting smaller, so that's the left side of the graph. And then as x approaches infinity, that means that x values are getting bigger, so that's the right side of the graph. Either way, like both sides of my graph, since it's an even degree and it has a negative lead coefficient, are going to go down. So both lines of my end behavior are going to go towards negative infinity, because that's, if f of x is going towards negative infinity, that means down. So both sides are going down. Okay, so I'm gonna stop. I'm gonna sketch my graph before answering the rest of them. I just think it's a lot. Like, even if the problem doesn't ask you to sketch it, it just seems like way easier to be able to figure out like where it's positive or negative, and where the relative max or min might be with the sketch in front of you. So let's see. I have my zeros. They're at 4, negative 1, negative 2.5, and 3. So do an x and a y-axis. Make this a little bit longer. And then my like largest 0 is 4, so I'm going to go up to 4. And then my smallest one is negative 2.5, so I guess I'll go down to negative 3. And then the y-axis, I'm not going to label. I'm not going to like scale it or anything. I may just add specific points, but I'm not going to label it because it's not going to end up being to scale. And again, this is just like very much like a sketch. It's not going to be perfect. It's just going to show like key features of the graph. So we can go ahead and we can put our like zeros on the function. So we'll do, there's one at x equals 4. Sorry, this was 1 and negative 1. There's one at x equals 4, and then x equals negative 1, negative 2.5, so like halfway between 2 and 3, negative 2 and negative 3. And then there is another one at x equals 3. So this is negative 2.5, this is 3, this is 4. And then I am going to go ahead and put my y-intercept on there just because we know it. I'm not going to worry about like scaling it or anything like that. I'm just going to put a mark. It's negative 30, so I'm going to put a mark on the negative side for the y-axis and then just label it negative 30 and put a point there. Okay, and then the rest of the graph we can fill in because the end behavior and figuring out what the multiplicity is. So first we'll talk about end behavior. So end behavior, we said both sides of our graph finish going downward. So for my like very far leftmost point, I'm going to draw a line going down, and then the right side goes down too. So for my very far right, like most x-intercept, I'm going to draw like a line going down there as well. And then multiplicity is like how many times a certain factor appears within your function when it's in factored form. So usually like if something has a multiplicity other than 1, if you look at the function in factored form, which is like how our original one was written, you would see exponents over the factors. So none of our like factors have exponents, so they all would be like an exponent of 1. So they all have a multiplicity of 1, which the main thing is that the multiplicity is odd. So if it's odd, on any given factor, you're crossing through at that 0 versus if it's even, you would bounce off of that 0. So since we don't have any even ones, we would just cross through every single one. So we would cross through, I'm going to start like on the left over here. So we would cross through at negative 2.5. At some point, we would turn back around and go through at negative 1. I'm going to make sure I hit the like y-intercept that I go through it. It's not necessarily like a point of like change in direction, but I just have to make sure I cross through it. At some point, I'll turn back around and I'll cross through at 3. At some point, I'll turn back around and I'll cross through at 4. So even though we don't know the exact points, this is like the general shape of the graph. So it could like go higher in some spots or lower in some spots. We have the correct intercepts, we have the correct end behavior. So this is enough to answer like where the function is positive or negative. So for where the function is positive, that means like where it's above the x-axis because all the y values are positive. So above the x-axis is right here and right here. So this section is between, like it starts being positive right here at negative 2.5 and it ends being positive right there at negative 1. So that would be negative 2.5 to negative 1. And remember, this is interval notation, so it goes like within parentheses or brackets. Brackets would mean that it includes that number. And for where it's positive or negative, we would never use brackets because at these like points where it's changing, it's not positive or negative. It's like at 0, so it's not included. So that would be our first interval. So negative 2.5 to negative 1. And then the second one right here, it starts being positive at 3 and it stops being positive at 4. So between 3 and 4. So the second one would be between 3 and 4. And then it's like, I know it looks the same as a point, but you just have to remember you're writing it like as interval notation. So this means like between x equals 3 and x equals 4. And it's always like when we're answering positive or negative, we're always just looking at like the x-intercepts because those are like the boundary lines of where it's going from like positive to negative or vice versa. And then now for negative, so there's this section right here that's negative, that's below the x-axis. There's this section right here, and then there's this section right here. So this one is like the left of negative 2.5. So the left of something would be like negative infinity to negative 2.5. Every value to the left of that. And then this middle section is like between negative 1 and positive 3. So between negative 1 and positive 3. And then this far right section is like from 4 all the way to the right of it. So 4 to the right would be like 4 to infinity. Like every possible x value after that, it's going to stay negative. So this would be negative infinity to negative 2.5, and then negative 1 to 3, and then 4 to infinity. So 3 different intervals here, like 3 different pieces where it's negative. And then for the relative max or min, you have to look at where the graph changes direction. So anywhere there's like a change in direction, there's going to be a relative max or a min. So like right here, it has to change direction. Somewhere around here, it has to change direction, and somewhere around here as well. So we can find like approximations for those numbers, because remember, like max and min are the y values. So we can just kind of estimate where those points would be and use the x coordinate from where the points would be to find the y value, but like find the estimated max or min. We'll just get into it. Okay, so like looking at this first point right there, that x value is like between negative 2.5 and negative 1. So I'm just going to estimate it as like negative 2. And then if I want to find like what the y value is there, I have to put that negative 2 into the function where x is. So it's going to go into like all of these. And that output, like what I end up getting, is going to give me the y value at that point. So we would find f of negative 2. And then we'll do the negative symbol in front. I'm just gonna like to save a little bit of space, I'll just kind of do it in my head as we go along. So negative 2 minus 4 for the first one, that'd be negative 6. And then if I put it in the second parentheses, negative 2 plus 1 is negative 1. And then the third one, x plus 2.5, would be negative 2 plus 2.5, so it'd be positive 0.5. And then the last one, x minus 3, would be negative 2 minus 3, so it'd be negative 5. And then to get my like output, I can count up all my negatives. I have 1, 2, 3, 4 negatives, so I have an even amount. So my output's gonna be positive, and I just need to multiply the like numbers together. So 6 times 1 times 0.5 times, sorry, my didn't multiply right, but 6 times 1 is obviously 6, and then times 0.5 is 3. So then 3 times 5 should be 15. So we got an output value of 15. So that means that this point that we were trying to find is like approximately 215. And again, it's like not exact. We don't really have a way of finding exact unless we had a graphing calculator. But it's enough. Like it's enough for the purpose of this problem. So then at that point, it's a high point. So it'd be a relative max. And then just because it's like higher than the points directly surrounding it. And then we're just looking for the y value there because it's like the height, like the highest point at that value, or the highest value at that point. So we have a relative max at 15. And then there's also going to be like another relative max over here because that point is another change of direction that's higher than the point surrounding it. So that one's between 3 and 4. So we could say like estimate at 3.5. And then we have to find the output value that goes with it. So we do it the same exact way. We would do like f of 3.5, and then is equal to, we're putting in 3.5 for like all of our x values in the function, so the negative will be out in front, and then it'd be 3.5 minus 4 is negative 0.5. 3.5 plus 1 is 4.5. 3.5 plus 2.5 is 6. And then 3.5 minus 3 is 0.5. Okay, and then now we can count up our negatives. We have like a even amount. We have two negatives. So our output's going to be positive, and we can just multiply everything together. So do 0.5 times 4.5 times 6 times 0.5 again is 6.75. So that means that the y value, like at this 3.5 point, is 6.75. And then it was a max at that point because it was higher than the points surrounding it. So we have a max at 6.75 and a relative max at 6.75. And again, just an approximation, like there could be a point that's like slightly above or slightly below it, but it's as much as we can do like manually without a graphing calculator. And then the last one, there's this point down here that's like lower than the points like immediately surrounding it. So there would be a local minimum there, or sorry, relative minimum. If you ever see that in the future, like local versus like relative, they mean the same thing. Just means like in regards to the points around it. So we can estimate that one having, let's say, like an x coordinate of 1, just to make it easier and give us an easier number to plug in than like a decimal or something. But it just has to be anything between -1 and +3. So 1 is in the middle of those two. We'll take that 1, we'll substitute it into the function to find f of 1. So don't forget the negative out in front of the function, and then starting with the first parentheses, 1 minus 4 is -3, and then 1 plus 1 times 2, and then x plus 2.5, so 1 plus 2.5 would be 3.5, and then 1 minus 3, so times -2, and then I have 1, 2, 3 negatives, so I have an odd amount of negatives, so my product will be negative, and then I can multiply the numbers together, so 3 times 2 times 3.5 times 2 again is -42. So this point is approximately 1, -42, and it's a low point in regards to the points around it, so that -42 is a relative minimum. Okay, so that was like an example that covers 16.1, 16.2, 16.3. Like those are all the concepts within the workbooks. So if you feel like you're good and you got it from that, I know we've kind of like repeated this like similar lesson a few times, but with different types of functions now. The next two examples are just going to be like structured the same way. So if whenever you feel like you get it, like feel free to kind of move on to like the work and stuff, and just know that like these extra examples will be here if you need them. So the next example, like same type of problem, just different function. Find the following key features of the function and sketch the graph. So our function is f of x equals -x minus 2 to the 4th power. So to find the y-intercept, same idea, we need to find f of 0. That means that we take 0 and we put it in the function where x is. So it would be equal to, don't forget the negative out in front, and then 0 minus 2 to the 4th power. And then negative 0 minus 2 is -2 to the 4th power. And then if I take -2 and raise it to the 4th power, it's like -2 times -2 times -2 times -2 times -2. I don't know if I said it 4 or 5 times. I'm sorry if I said it 5. But anyways, -2 to the 4th power is a positive 16. And anytime you have like a negative number raised to like a even exponent, it ends up being positive. But I have to carry down this negative. So it ends up being -16 after all. So we have a y-intercept at 0, -16. And then for the x-intercepts, or I'm getting ahead of it, for the zeros, we put 0 in for f of x. So like completely replaces it. So it's be 0 equals negative x minus 2 to the fourth. And then we want to solve for x. This is already in factored form, so I just need to set the factor equal to 0. Don't have to do anything with the negative. The only factor that's really there is the x minus 2. The fact that it's like being raised to the fourth power does impact the graph, but when we're finding the zeros, we just have to do like 1 x minus 2 equals 0, like set that one factor equal to 0, because if I did it 4 times, I would get the same 0 every single time. So then from there, I can add 2 to both sides. My goal is to get x by itself here, so this would be an x equals 2 for my 0. And then zeros and x-intercepts are the same. We'll just write the x-intercept as a point. So it'd be 2, 0. For end behavior, we are looking at what the lead coefficient would be and looking at if it's positive or negative. So if we were to take like this whole thing and expand it, there would be like 4 different x minus 2's. And then that would mean that we're taking that x and we're multiplying it by x like 4 different times, like x times x times x times x. So the lead coefficient would end up being just like 1, but because it'd be like a 1x to the fourth, but because that negative is there, it'll end up being negative. The negative will just stay out front the entire time. So it has a negative lead coefficient and it's a quartic function, so it has a like even degree. So anytime your function has an even degree, like quartic or quadratic, that means that both ends will go in the same direction. So both ends in this case will be going down. So both sides go down if it's like negative. If it's positive, both sides would go upward. Okay, so we have a negative lead coefficient. That's enough to help us determine our end behavior. So since both sides go downward, that means that both of our f of x's are going to go to negative infinity, because that's what down is in terms of end behavior. So this is like basically as the graph goes to the left, it goes down. As the graph goes to the right, it goes down as well. And then from there, we'll go ahead and sketch the graph before we answer like the rest of it. So I just have the one like x-intercept at 2, so I don't have to like make my x-axis super long or anything. Let's see. Don't even really need a negative x-axis. Okay, so we'll do 1, 2, and then I'm not gonna like scale the y-axis completely, but I am gonna just go down and like put a mark and call it negative 16, even if it's not exactly to scale, so that I can put my y-intercept on the graph. Then I'll go ahead and plot my points that I know. So I know that there's an x-intercept at 2, 0, so I'll put one right there. And then I know that there's a y-intercept at 0, negative 16, so I'll put a point right there. And then the rest we can determine from like the end behavior. And this is like really not to scale as I'm looking at it, but it's okay. So the left side of my graph goes downward. So from my leftmost x-intercept, y-intercept does not really like impact things here. We just want to make sure that we cross through it because we know it's on the graph. So from my leftmost x-intercept, I would go downward, but there's only like one x-intercept. And if like the left side of my graph is supposed to go down and the right side of my graph is supposed to go down, that just means that like from that x-intercept, like from 2, like both sides are going downward. Like that. And then this kind of like happened naturally because like we only had the one x-intercept, so I had to go down from like both sides of it, left and right side. But if we think back to like multiplicity, the like factor, or not factor, but yeah, the factor, x minus 2 was being raised to like the fourth power, which is an even number. And when you have an even like power, even multiplicity, it's supposed to bounce off of the x-intercept at that point, as opposed to like crossing through it, you know? And it certainly does bounce off of it. And then one other thing to keep in mind, if it's just a sketch, it's not that big of a deal, but usually like the higher the power, the more the graph kind of like sticks along that point. So like see how like I drew my sketch like kind of like sticking along it, like staying up near it before dropping off. That's not like that crucial for like sketching the graph and stuff like that, but it's kind of nice to know like how it changes the shape overall. Okay, that's our sketch. So if we look at the graph, it's not like if we're trying to determine where the function is positive, at no point is it above the x-axis. Like there's no points up here. So it's not positive at all. So I'm just going to put NA for positive. And then for negative, it looks like it's negative like all throughout. However, this point right here is the point 2,0. So negative is referring to the y value. Like we look above and below the x-axis because that's where like y is positive versus negative. But like at this point, the function isn't positive or negative, it's 0. So we can't just say like everywhere. Like we can't say, don't write this because it's wrong. We can't say like negative infinity to positive infinity is where it's negative. We actually have to write it in like two different parts. So it's negative from here to here, and then at 2,0, it's not negative, it's at 0. And then we have to write this as like a separate section. So this left side is like negative until we get to 2. So the left side of 2. So negative infinity to negative, or sorry, to positive 2, excuse me. And then this side over here, it's like starts being negative again after 2, and then everywhere to the right. So that'd be 2 to infinity. So for negative, we would say negative infinity to positive 2. And then positive 2 to infinity. So just because like at that x-intercept it's exactly 0, we can't describe it as like one consecutive section. We have to like make it two different sections. Okay, and then the last part is the relative max or min. So there's anywhere there's a change in direction, there's a relative max or min. So we can see there's only like one change direction on this graph. It's like right here, because there's no other like bends or anything like that throughout the entire function. So since that point is like higher than the point surrounding it, that would make it a relative maximum. And we already know that point, so we don't have to like do the work of finding it. The relative maximum is the y coordinate 0. So the relative maximum is 0. And technically that would be like a maximum in general. It wouldn't even be relative, it'd just be the whole thing. The maximum of the entire function. And then there is no relative minimum, like there's no low points because there's no other changes of direction. And this graph just like continues to go down forever, so it'd be infinity. And when we look for relative max or min, we're looking for like actual like values rather than just like infinity. So for relative max or relative min, just write none. Okay, and then I'm probably going to like cut this example out and make it like a separate video. Otherwise the video would be like super long. Okay, so just know there will be some few extra examples. They all are pretty much like the same problem. They just have a different function that we're working